Safety engineering is an engineering discipline which assures that engineered systems provide acceptable levels of safety. It is strongly related to industrial engineering/systems engineering, and the subset system safety engineering. Safety engineering assures that a life-critical system behaves as needed, even when components fail. Analysis techniques can be split into two categories: qualitative and quantitative methods. Both approaches share the goal of finding causal dependencies between a hazard on system level and failures of individual components. Qualitative approaches focus on the question what must go wrong, such that a system hazard may occur, while quantitative methods aim at providing estimations about probabilities, rates and/or severity of consequences. The complexity of the technical systems, such as improvements of design and materials, planned inspections, foolproof design, and backup redundancy, decreases risk and increases the cost. The risk can be decreased to a LARA as low as reasonably achievable or a LAPA as low as practically achievable levels. Traditionally, safety analysis techniques rely solely on skill and expertise of the safety engineer. In the last decade, model-based approaches have become prominent. In contrast to traditional methods, model-based techniques try to derive relationships between causes and consequences from some sort of model of the system. The two most common fault modeling techniques are called failure mode and effects analysis and fault tree analysis. These techniques are just ways of finding problems and of making plans to cope with failures, as in probabilistic risk assessment. One of the earliest complete studies using this technique on a commercial nuclear plant was the WASH 1400 study, also known as the Reactor Safety Study or the Rasmussen Report. Usually a failure in safety-certified systems is acceptable if, on average, less than one life per 109 hours of continuous operation is lost to failure. As per FAA document AC 25.1309-1A, most Western nuclear reactors, medical equipment, and commercial aircraft are certified to this level. The cost versus loss of lives has been considered appropriate at this level by FAA for aircraft systems under federal aviation regulations. Once a failure mode is identified, it can usually be mitigated by adding extra or redundant equipment to the system. For example, nuclear reactors contain dangerous radiation, and nuclear reactions can cause so much heat that no substance might contain them. Therefore, reactors have emergency core cooling systems to keep the temperature down, shielding to contain the radiation, and engineered barriers, usually several, nested, surmounted by a containment building, to prevent accidental leakage. Safety-critical systems are commonly required to permit no single event or component failure to result in a catastrophic failure mode. Most biological organisms have a certain amount of redundancy, multiple organs, multiple limbs, etc. For any given failure, a failover or redundancy can almost always be designed and incorporated into a system. There are two categories of techniques to reduce the probability of failure. Fault avoidance techniques increase the reliability of individual items, increase design margin, derating, etc. Fault tolerance techniques increase the reliability of the system as a whole, redundancies, barriers, etc. Safety engineering and reliability engineering have much in common, but safety is not reliability. If a medical device fails, it should fail safely. Other alternatives will be available to the surgeon. If the engine on a single-engine aircraft fails, there is no backup. Electrical power grids are designed for both safety and reliability. Telephone systems are designed for reliability, which becomes a safety issue when emergency, for example US 911, calls are placed. Probabilistic risk assessment has created a close relationship between safety and reliability. Component reliability, generally defined in terms of component failure rate, and external event probability are both used in quantitative safety assessment methods such as FTA. Related probabilistic methods are used to determine system mean time between failure (MTBF), system availability, or probability of mission success or failure. Reliability analysis has a broader scope than safety analysis, in that non-critical failures are considered. On the other hand, higher failure rates are considered acceptable for non-critical systems. Safety generally cannot be achieved through component reliability alone. Catastrophic failure probabilities of 10-9 per hour correspond to the failure rates of very simple components such as resistors or capacitors. A complex system containing hundreds or thousands of components might be able to achieve MTBF of 10,000 to 100,000 hours, meaning it would fail at 10-4 or 10-5 per hour. If a system failure is catastrophic, usually the only practical way to achieve 10-9 per hour failure rate is through redundancy. When adding equipment is impractical, usually because of expense, then the least expensive form of design is often inherently fail-safe. That is, change the system design so its failure modes are not catastrophic. Inherent fail-safes are common in medical equipment, traffic and railway signals, communications equipment, and safety equipment. The typical approach is to arrange the system so that ordinary single failures cause the mechanism to shut down in a safe way. For nuclear power plants, this is termed a passively safe design, although more than ordinary failures are covered. Alternately, if the system contains a hazard source such as a battery or rotor, then it may be possible to remove the hazard from the system so that its failure modes cannot be catastrophic. The U.S. Department of Defense Standard Practice for System Safety (MIL STD 882) places the highest priority on elimination of hazards through design selection. One of the most common fail-safe systems is the overflow tube in baths and kitchen sinks. If the valve sticks open, rather than causing an overflow and damage, the tank spills into an overflow. Another common example is that in an elevator the cable supporting the car keeps spring-loaded brakes open. If the cable breaks, the brakes grab rails, and the elevator cabin does not fall. Some systems can never be made fail-safe, as continuous availability is needed. For example, loss of engine thrust in flight is dangerous. Redundancy, fault tolerance, or recovery procedures are used for these situations, for example multiple independent-controlled and fuel-fed engines. This also makes the system less sensitive for the reliability prediction errors or quality-induced uncertainty for the separate items. On the other hand, failure detection and correction and avoidance of common cause failures becomes increasingly important to ensure system-level reliability.